All right, so let me continue about quadratic optimization, right? So basically, the optimization problem that we saw in the previous part, it makes perfect sense, but it's not a typical optimization problem that we learn how to solve. So now I am going to explain how this unusual optimization problem can be converted to something familiar. Okay, so if let's say my vector W, well, is a column vector W1, W2, and so on, WP, and my vector X is also a column vector X1, X2, and so on, XP. Then I can rewrite my hyperplane equation in this form. So W transpose X plus B equals 0. So at the same time, and this is going to be important, that if you take W transpose times W, this is the same as the dot product of W with itself, and this is the square of the norm of W. Right, so this is our classifier associated with the separating hyperplane. Now, the functional margin, so what we call this functional margin, is yi. So remember that yi is either -1 or 1. And the sign of yi shows on which side of the separating hyperplane our observation is. Okay, and the functional margin of the entire training data set is this sum. So basically here, y is this vector y1, y2, and so on up to yn. So this is the vector of the size n, capital times n, and x is the matrix of our training data, right? So every column, so every row here is one observation. So this is one observation. So x is a matrix of the size n times p. Okay, so this is the functional margin of the entire training data set. Now, the distance from a point x to the hyperplane is given by this equation. Okay, so again, recall that W is the vector perpendicular to the hyperplane, so this is W. Now, if we take any training observation, say, well, actually it doesn't matter. So now it doesn't have to be a training observation. So if we just have any point x, right? So then how do we find the distance? So we need to draw perpendicular from x to our hyperplane, and then measure the distance from our point to the base of this perpendicular, right? So, and this distance r is given by this formula. Now, why is this so? I'm not sure if you have seen this equation before. Probably you have, at least in some context, or maybe for a two-dimensional plane, or maybe for the space. We are going to prove it in tutorial. Okay, so this equation we are going to just prove in tutorial. It is a very nice exercise, I think. So later we will prove that it is formula. Now, if the norm of the vector W is 1, so which means that the dot product of W with itself is 1, so, or in the matrix form, W transpose times W is 1, where W is a column vector, right? So then basically this one disappears, and the functional margin is going to be precisely the distance. So why is this so? Because you know, this yi is going to be either 1 or -1, right? So, and it is going to be 1 if the other term is positive, and -1 if the other term is negative. So in either case, when we multiply yi by this, we're going to get the absolute value of this term. So this is why it is the same thing as this absolute value. Okay, so which means that our functional margin is going to be precisely this distance from our training point to our hyperplane. So this is R. Well, Ri. Okay, so the distance from our training point to our separated hyperplane. Okay, so and in the in part 2 of the lecture, so what we did, we defined this optimization problem. So we maximized this number m such that all distances from all training points to our hyperplane are bigger than m, right? So now we know that this is actually the distance. So Ri is the distance from our xi to our hyperplane. And we just want to maximize it such that the norm of the vector w is fixed. And now we're going to rephrase it a little bit, right? So instead of maximizing the right-hand side of these inequalities, keeping the norm fixed, we're going to minimize the norm, keeping the right sides of the inequalities fixed. And this is how. So this is how this is going to work. So let me explain. Right, so one more time. So the distance from our Ri is the distance from the ith training point to the hyperplane. This is given by the equation yi times w transposed xi plus b over the norm of w. Right, so which is 1 over our norm of w times this yi times wt xi plus b. Okay, now this is our functional margin. What we are going to do, we are going to just keep this fixed. So we are going to write that this is some fixed number, say 1, and we are going to maximize the other term. So previously we assumed that this term was 1 and we maximized this term. But of course, equally, equally well, we can keep this one fixed and maximize this one. Okay, but so which means that we're going to maximize the reciprocal to the norm of w. But doing it is the same as to minimize the norm of w. But to minimize the norm of w is the same as to minimize the square of the norm. And usually we also add 1/2 here. I mean, of course, it doesn't affect the final answer, but it's just for some differentiation, it's more convenient to halve it. So, and this squared norm of w is just w transpose times w, so 1/2. Okay, so it means that finally what we get is that our optimization problem is to minimize the square, well, half of the squared norm of w, subject to the following constraints. So subject to, well, this is our constraint. So yi functional margins should be times xi plus b. Well, I wrote equals 1, but it is going to be precisely equal to 1 only for points that are exactly on the margin. So for all other points, they will be strictly bigger than 1. So I am going to write bigger than or equal to 1. Okay? And this is the final standard quadratic optimization problem for support vector. Well, now we call it the maximal margin classifier, but in the next part we will see that later it's going to be called support vector classifier. Okay, so this is the final optimization problem. Now let's let me just explain why this is better, right? So this is better than the original because this is something familiar, right? So the objective function is quadratic in w, right? So if your w is something like x, y, z, then this part is going to look like minimize x squared plus y squared plus z squared, right? And this part is linear in W, right? So because W only appears here, so this part is going to be some linear inequality on W, something like minus x plus 3y minus 5z is bigger than minus 22.5 or something like this, right? There will be several of these. So strictly speaking, that there is going to be n capital inequalities like this. But in any case, this is something familiar, right? So because, you know, in the case of just one objective function and one inequality, you probably saw it in calculus. You saw some questions like this in calculus. So find the maximum or the minimum of some function subject to certain constraints. So the more generally, if you took this basic optimization course, then you probably are more familiar with this. So from Prof. Cho or from Prof. Yan. So Prof. Yan is now teaching, right? So this has to do with some conditions. So there is a big theory behind it. So my point being is that I'm not going to teach you how to do it because it is fairly complicated and there is a big theory. But the important takeaway is that this is a standard problem in the theory of optimization, and people know how to solve it. Okay, so which means that finding our maximal margin classifier is reduced to this quadratic optimization, which is known how to solve. Now, I'm going to just tell you it without proof that the solution of this minimization problem is going to be a linear combination of certain, not all of them. So notice that this is the sum over a subset of the vectors, and these are actually support vectors. So this S is support vectors. So this S is the set of support vectors. Right? So if let's say if we have 5 support vectors, then this W is going to be a linear combination of these 5 support vectors. So B can be found from the equation. So you know that. So we know that W transposed X I plus B is 0 if I is a support vector. And this is how I got this equation. And here is the final classifier. Now, the important part here is that the final classifier, in order to apply the final classifier to a new data point, what you do is you calculate the dot products of your new data point with all the support vectors. And then you just apply this classifier. So you take the same alphas, and in R it is possible to just extract and print all these alphas. So you just apply the same alphas, and then you take the sign of the resulting expression, and then this is going to be your final classifier. Okay, so I hope it was clear. So please do the quiz.